Welcome to another exciting episode of AP Chemistry here at Spain Park High School. If you're enjoying these exciting videos, please feel free to subscribe to my channel and hit that like button. All right, today is Monday, February the 27th. Now, just so you know, we need to be finished with this unit by the end of February to be on schedule, okay? That's probably not gonna happen since this is a short month. I don't think we're gonna be finished by tomorrow, okay? But we're gonna keep pushing. We got 3 units left to go: equilibrium, acids and bases, and electrochemistry. Getting close, but we don't have a whole lot of time left considering we got March and April, and we were supposed to be reviewing for 3 weeks in April, and well, we got a week of spring break in there, and we have e-learning days and all these other things. So that means we need to press on quickly, okay? This stuff here, equilibrium, this general equilibrium is not super intense, okay? So we should be able to go through this fairly quickly. So what is the definition of equilibrium? Equilibrium, okay? In general, it's the forward rate of reaction equals the reverse rate. Of reaction. Okay? Forward rate equals reverse rate. You need me to sign me up? You get ready for the semis? Okay? Put me on the team. I'm ready. Put me in, coach. Okay. Forward rate of reaction equals reverse rate. Now, if you want to look at a fancy definition, you look at the top of those fancy notes that I just gave to you. It gives you a complete full definition. But the key here is that it's the rate of the reaction, not the concentrations that are the same. So if we look here at, let's just say this represents all of our reactants. Can you see this on the video?
Yeah.
Okay. All of this represents the reactants, and all of this represents how much products. Well, at the start of a reaction, we don't have any products. Everything is a reactant. Okay? So I'm going to use two 250 milliliter beakers, and obviously when the reaction first starts, there's nothing there to go backwards, so it only goes forwards. Okay? So now I scoop again, and I have very little reactant, okay? So I might get, just a little bit came back, okay? But now I keep scooping, so scoop, a little bit more came back, okay? Keep scooping. Now I'm getting a little bit less of the reactants and going back. Keep scooping, okay? Going here. Still the forward rate still way faster than the reverse rate, okay? Pour, pour, keep going, pour, pour. At some point, okay, they're getting closer. It's a race, okay? Now I have about 150 versus 75. Pour, pour, okay? That one a very good scoop. Let's try that scoop again, okay? Pour and pour. So now, they're getting closer. So the forward reaction is slowing down. The reverse reaction, now we pretty much have exactly the same amount. So now, no matter how many times I scoop, if I'm scooping out the same amount from both sides, I'm going to end up having the same amount on both sides. Now, because I'm using the same amount, the forward rate, reverse rate, we're ending up with just about the same amount of reactants and products. And that's what we tend to want to think of with the equilibrium, that they end up 50-50. But that's not necessarily true. What happens if I use this beaker, but only this one? Can I reach equilibrium? Again, nothing here, so it can only go one direction. Now when I scoop, I got a little smidgen. Okay, scoop again, okay? I can get a little bit more. Scoop again. This is where I wish I could watch myself at 1.5 speed here. Okay, so pour and scoop. Now little by little, I'm starting to get more product, but the forward rate still going way faster than the reverse rate. Okay, pour, keep going. Okay, now I have about 125 there, and I have about, 40 there. Okay, keep scooping. Forward rate and reverse rate. Now I'm at not a whole lot different. Okay, kind of just keep going. Okay, now I'm right about 100 and 100. This is the 100 ml beaker, so I'm pretty close to right exactly the same now. Okay, so every time I'm scooping, I'm getting about 100. This is right at the 100. This is just about full. It's right about the 100. So now I'm going to be staying at equilibrium. What does that mean about the amount of products and reactants? There's a lot more products now than there are reactants. We're still at equilibrium. The forward rate now is equaling the reverse rate, 100 milliliters going both ways, but we have more products than we do reactants because the forward rate, it's more of a product favored reaction now. So equilibrium doesn't mean we have to have equal amounts of reactants and products. It just means that once equilibrium is established, for every one that comes this way, some comes back that way. It just takes a while. So our equilibrium is the forward rate, not the amounts. It's all about the rate. And that's what we learned in kinetics with our fast equilibrium, that the forward rate equal the reverse rate. We had to know that in order to be able to do those fast equilibrium proofs that y'all loved so much. So let's look at the notes then. So if I'm looking here, first off, we're talking about a dynamic equilibrium. What's the word dynamic mean in this case? Changing, okay? It's a dynamic equilibrium. Is that a water bottle? Yeah. Chunk. Okay? So when I'm looking here, if I kept this from Sam and I just kept it for a year and the top's on tight, I keep it for a year, will this water level still be here? Okay. Will it all evaporate out?
No.
Is there anything above the liquid right now?
Yes.
What is above the liquid? There's some water vapor, right? So when he took, I'm not going to do it, but when he takes the lid off and takes a swig, pretty much all that water vapor comes out. He puts the lid back on. Now the water begins to evaporate. Okay, but there's not a whole lot up there, so it's the rate of evaporation is pretty much the only direction. But then more and more molecules of water start collecting up in here, and then we can start seeing the rate of condensation beginning to increase, until finally the concentration gets great enough up here to where the rate of evaporation and the rate of condensation equals, and so then our concentrations remain the same number of vapor molecules up here, and therefore the same number of water molecules basically down here, but it's constantly changing. Some are evaporating, some are condensing. It's a dynamic equilibrium. In a chemical equilibrium, the same thing. They're constantly going back and forth, but their concentrations end up remaining the same. Now, we talked a lot about vapor pressure. What causes pressure in general? Collisions with container wall. Okay, so there's a certain number of collisions taking place. Once the equilibrium is established, there's a certain concentration that stays the same up here. The forward rate and reverse rate are equal, so we have an equilibrium vapor pressure inside the bottle. Now, what happens if I put this out in the trunk in the summertime, or I heat it up somehow? What's going to do to the rate of evaporation? It's going to increase. So at first, the forward rate is going to all of a sudden increase, and we're going to have a whole lot more. But then the concentration is going to get great enough up here to where the rate of condensation starts speeding up as well. And then the forward rate and reverse rate have now equaled one another, but at a faster rate. But we now have more molecules up here. So what does that mean about my equilibrium vapor pressure? Has it gone up or down or stayed the same? Up. If I increase the temperature, that vapor pressure has increased in temperature. I've changed the position of the equilibrium, but it's still at equilibrium, just with a different number of molecules. Okay? But that's what a dynamic equilibrium means, that it's constantly changing. The concentration stays the same, but the molecules themselves are different. All right? So, if I look at this plot right here, obviously we have 0 products to start with, and I have all reactants. Well, as the reaction goes, the reactants concentration decrease. Why is this not linear?
The rate of reaction
It slows because there are fewer and fewer reactant molecules, so the number of collisions are becoming less and less, and we talked about the effect of collision and all that last unit. And then the same in reverse, the rate of the reverse reaction, okay, we're getting more and more because we end up having more and more products. We don't have hardly any to start with, but then here, so when's equilibrium established though? When the rates are equal. How do we know the rates are equal? What happens to the slope? It goes to 0. All right? Because now my concentration, once equilibrium is established, now the forward rate and reverse rate, we end up having the same amount, so the concentration then ends up staying the same. Now, which one do we have more of here, reactant or product? Let's just even say, assume here that this is A, this is B, this is C, and this is D. How does the rate of the reaction, which one do we have more of at the end? Once equilibrium is established, which one do we have more of? Products. I mean, and this is just, it's higher up on the concentration, so we've got a greater concentration of products than we do reactants. If we had equal amounts, what would that look like? Okay, I liked your hand signals, but can you say it in words?
Not really. Like C and D would like move to a point in between A and B, and A and B would go to the same point.
So it ended up looking more like, let me do it in blue. It's going to look like this. I think that's what you were saying. Okay? So they're just going to end up being the same amount. What would it look like if reactants were favored? That's right. It's going to end up looking like this and like this. Okay? To where you end up having more reactants than you do products. It doesn't matter which one, and we're going to learn how to tell which one is more, but we can just tell from our graph. But the key is equilibrium is established once the line goes flat. That means concentrations are no longer the forward and reverse rate now equal one another. Concentrations are constant, not equal, but constant. Okay? All right. That's just being able to interpret a graph. Now, let's talk about the equilibrium constant. Now, I don't know necessarily who did these notes. They're just pretty, and I copied them offline. Actually, it's the National Math and Science Initiative. But we can't really talk about the significance of K until we talk about this right here. Our equilibrium expression. Okay? It's known as the law of mass action. But no one is going to call it that. They're just going to call it the equilibrium constant expression. The official name is the law of mass action, okay? Equilibrium constant. Now, in your equilibrium constant, the coefficients become your exponents. So if I look at that equation that they just gave, which was was it CO plus H2? Is that what it is? Right there by the graph? CO plus H2O goes to CO2 plus H2. Gas, 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 and gas. All right? If I'm going to write my equilibrium expression, I'm going to say KEQ is going to equal my concentration of my CO2, but it's raised to the first, times H2 raised to the first over CO times H2O. So that's KEQ. But what is that? Anybody remember what brackets mean? Concentration in terms, I heard somebody say in molarity. So that means the concentration of whatever those things are in molarity. But it's always products over reactants. The coefficients are raised to a power. All right? So, because I'm giving this in terms of concentration, this is what we also refer to it as Kc. C stands for concentration in terms of molarity. Now, I could also do it in terms of Kp. What do you think P stands for? Pressure. I could put the units in terms of pressure. Since this is an all gas equilibrium, I can say that Kp is going to equal the pressure, the partial pressure of the CO2 times the pressure of the hydrogen divided by the pressure of the CO times the pressure of the H2O. Now obviously, Kc is measured in terms of molarity. Kp is going to be measured in pressure. Now there's no constant in here. So pressure can be in any unit. It can be atmospheres, it can be millimeters of mercury, it can be any unit because there's no constant. Generally it's going to be atmospheres or millimeters of mercury. Okay? So they're measured in different units so they do not equal one another. Now there is an equation that relates the two together, but you no longer have to know that. It's not on the AP test anymore. It's just really plugging into an equation. It uses the ideal gas law constant R, and in there, and actually on the third page of these notes, they kind of discuss how to do that, but we're just going to skip over that. All right? So, but this is a ratio of products over reactants. So, if I'm looking at that ratio, well, I'm not even going to go there for I'm going to come back to that, the meaning of K, once we do some problems. Okay? So, I'm really trying to go fast today. I'm going at 1.5 speed. If I look then down here, and I want to cover up my answer, let's just look at this exercise 1. I want to write my equilibrium expression for this. Well, if I write it in terms of Kc, it's always going to be products over reactants, coefficients raised to powers. So my products, NO2, what do I raise that to? To the 4th, times H2O, raised to the 6th, all over NH3 raised to the 4th times O2 raised to the 7th. Now, when we write these expressions, we ignore, and it doesn't apply here, but ignore solids and liquids always. Their concentrations are said to be constant. They're figured into the equilibrium constant. So if there's a solid or a liquid in the equilibrium expression, we just ignore it. You don't include it. Okay, just trust me, that's the way it works. Now what would I say, how would I write Kp for this? The pressure of the NO2 raised to the 4th power times the pressure of the H2O raised to the 6th power divided by the pressure of the NH3 to the 4th power times the pressure of the O2 to the 7th power. I like my equals in the middle. So the only thing that's different between KC and KP is, are we measuring in molarity, or are we measuring in atmospheres or millimeters of mercury? But we don't put the pressures in brackets. Brackets always mean molarity. If we're dealing pressure, we just use the partial pressure with the subscript. Okay? Some teachers or whatever books will put it PNO2 in a parenthesis to the fourth. I think that's extra work to have to write it like that. Okay? But you'll see it written like that a lot with it just being in a parenthesis. But it's the exact same thing. It's the pressure to the fourth. Okay? So, that's our equilibrium expression. So if I go down now, and I do these next two, now, I'm not worried about you being able to write out, okay, the equation. Solid phosphorus pentachloride. What would the formula of phosphorus pentachloride be? PCl5, and it's a solid. It's going to be in equilibrium, okay? The decomposition to liquid phosphorus trichloride, so it's going to be PCl3 liquid plus chlorine gas, and chlorine is one of our 7 diatomics, so it'd be Cl2 gas. So what's my Kc going to be? That's it. Kc is going to equal the concentration of Cl2. What would Kp be? The pressure of the Cl2, and it's just to the first power. So you calculate Kc or Kp. All right, B, it's a little bit fancier. Deep blue solid copper 2 sulfate pentahydrate. Woo! What does the Roman numeral 2 tell us? I heard mumbling. Oxidation state is what? It's being what? The copper's oxidation state's +2. So it's Cu plus 2 plus, what's sulfate? We've all know sulfate now. SO4. And anything with sulfur in it has what charge? -2. So it's just going to be +2 and -2. 2 plus, it doesn't matter which way you put the sign. Okay? Now what's pentahydrate mean? Okay, but times, how do we represent the times? A dot. Dot 5H2O. Remember at the beginning of the year we did we evaporated the water off. We got the percent water, the empirical formula of a hydrate. Okay, so we heat that up, and that's a solid, and that goes to white solid copper 2 sulfate plus water vapor. We don't have vapor and a gas of the same thing. Anybody remember the difference between a vapor and a gas? It's water vapor, but oxygen gas.
One's a liquid, just like
Say it again.
one's like this liquid that's dispersing the air.
Okay, it's not a liquid dispersing air. It's still a gas, but you're on the right track.
It's like when it's like heated up and when it's like the device.
Okay, you're warmer. Not that you're heating it up, but you're warmer. Okay? Water vapor, alcohol vapor, Vicks vapor rub.
What happens when a liquid goes in a gaseous state?
Okay, a liquid or a solid that's at room, normally a solid liquid or a solid room temperature becomes a gas, we call it a vapor. If a substance is already a gas at room temperature, carbon dioxide, oxygen, nitrogen, then it's a gas. They're both gases, it's just what's their state at room temperature. Okay? Some substances that are solids or liquid at room temperature that are in the gaseous phase are called vapors, but we still represent with a G. So what's my Kc going to be? H2O to the fifth, and Kp is going to be the pressure of the water to the fifth. Okay? You just ignore solids and liquids. Everybody with me so far? So just writing the equilibrium expression. So if a question ever asked to write the equilibrium expression for the given reaction, all you do is that. Products over reactant, coefficients raised to power, ignore solids and liquids. Okay, no numbers go in, you don't have to solve for anything. The equilibrium expression is just that. All right, moving on. So let's look at this. $52, right? Okay.
Today's 47 since Monday.
It's 47? Oh, man, Monday's supposed to give me more. I know it does, but. Okay, so this is here. The following concentrations were observed for the Haber process. Now, I guess they assume you know the Haber process. If you recall back in first semester, I gave you a bonus reading opportunity to read about Fritz Haber. He was a German. He was known for coming up with all these war gases. He was not a good person, but he did come up with a way to make ammonia. The Haber process looks like this. Okay, so that's, what's an equilibrium though. Okay, so that's the Haber process. So the first thing is calculate, and since all of these are in brackets, molarity, what do we want to calculate? It just says K, but what are we really going to calculate? Kc. What's the expression just going to be? What's it going to be? What over what? Products over reactants. NH3 squared over N2 times H2, what? To the cube, to the third power. So that's my equilibrium expression, but now they give you all the equilibrium values. So we're going to find that there's 3 ways to solve for K given concentration information. This is the first, the easiest, the one you'll probably never see. Okay? Because it's just plug and chug. Okay? So we go in and we just plug in NH3. Now I don't know why they said 31 times 10 to the minus 2, but what would that be just in a decimal? Just 0.31, right? Squared. Divided by 8.5 times 10 to the minus 1 is 0.85. And that's to the first, times 0.0031, and that's going to be cubed. So somebody get me an answer for that. Well, that's what the answer says, but that's not what they got in 3.8 times 10 to the 6th. Okay? Now, the reality would be it's molarity squared divided by molarity times molarity cubed. So it'd be molarity squared divided by molarity to the 4th, which means it'd probably be molarity to the minus 2. However, we never have to worry about units on K. With kinetics, the units are always asked for. Equilibrium, since it changes every time, they never ask for units on K. All right, so that's what K would be at 127. This is what equilibrium. Now, because this is a ratio of products to reactants, and we get that big number, which one do you think we have more of once equilibrium is established? Way, way, way more products. Okay? It's a big number. There you go. And again, it's numerator versus denominator, products over reactants. Since the number is very big, that means the numerator is way bigger than the denominator. Way more products than we do reactants. So this would be a very product favored. If K is greater than 1, go back to the first page, K is greater than 1, it's going to be a product favored reaction. If the reactants are greater than the products, what's going to happen to the value of K? Less than 1. It'll be a 10 to the negative something. Less than 1. That means the reactant favored. If K equals 1, is going to be very, very rare. Okay, that means about equal amounts. Now, let's look here. What's the difference between this equation and that equation? Everybody look. Everybody look. What's the difference between this equation and this equation? They're just reversed, right? The coefficients are all the same, it's just reversed. So what does that mean about products and reactants? So what does that mean about the value of K? Okay, after all the mumbles, I heard reciprocal. Okay? What's the reciprocal mean?
1 over.
1 over, because reactants have become products, products have become reactants. So when we flip an equation, because the equation is reversed, K prime is equal to 1 over K. So K prime, in other words, just the new K, is going to equal 1 over 3.8 times 10 to the 6th. And what's that going to equal? So what? 1, no, because 1 over 3.8 is going to be some different number. 2.6 times 10 to the minus 7. Now notice again, 10 to the minus 7th. Is that a big number or a small number? Very small. So is this going to be a reactant favored or a product favored? Very reactant. Now notice again, here the ammonia. So this reaction favors producing ammonia. So if you already have ammonia, it wants to stay ammonia. If you don't have ammonia yet, it wants to make the ammonia. Okay? So depending upon how you write it, okay, you get a number, a big number or a small number, telling us which direction the reaction is going to lie, which one's going to have more product or favor. Okay, so that's what, when we look over here on our acids and bases relative strength chart, we can see that for our strong acids, what makes an acid strong? What about it?
100% ionization.
100% ionization. So the K is so large, you have almost all product, very little. You know, what happens when you divide by 0? Okay, doesn't Mr. Sandlin say your calculator blows up or something? You know, because you have, so it's so big we can't even calculate it because it's nearly 100%. But as you go down, there's less and less dissociation, so there's less and less product. So K is getting smaller and smaller as the acid's getting weaker and weaker. It's telling us the degree of ionization. How far is the equilibrium lying on the product side? Everything below oxalic acid and below, they're all negative, which means there's more molecules than there are ions. It's more reactants than it is product. Okay? That's what K tells us, the position of the equilibrium. Now, as you go down to this next one, the next one says, and I'm just going to do it in red. You can see it on your notes, but I don't want to change this. It says multiply it by 1/2. So I get 1/2, I get 3/2, and I get 2/2, which basically means 1. So I multiplied the equation by 1/2 to get that equation in C, correct? Does everybody see that? How do we use coefficients in our equilibrium expression? As exponents. So what do we have to do to the value of K? We have to raise it to the 1/2 power. Okay? So it's this equation right here, so it's this value, it's still left to right, but multiplied by 1/2. So for C, and I don't want to erase it, over here for C, it's going to be K double prime is going to equal 3.8 times 10 to the 6th times 10 to the power of 6 raised to the 1/2 power, which is square root. Okay, but whatever you do to the equation, if you multiply it, because coefficients are your exponents, you raise the value of K to that power. So what is that, just so you can plug in an answer in your space? Anybody get it?
1,203.00.
So just give me 2 sig figs in scientific notation. 19,000, so 1.9 times 10 to the 4th is 19,000, right? So 10 to the 4th.
No,
It says 10 to the 3rd.
10 to the 3rd? So 1,900, 1,900. Okay, so go back up to the top of the page then. This is super important. This is multiple choice questions over and over and over again. Changing your stoichiometric factors. That means multiplying and changing your coefficients. You raise the value of K to the power of the multiplication factor. We raise it to the 1/2 power. Okay? If you reverse an equation, you take the reciprocal. And then if you add equations, and we'll get this will really be more important in acids and bases when we have di and triprotic acids. You multiply K's if you add the equations together. So if 2 equations add together to give you a third, the 2 K's will multiply to give you the K of the third.
The answer?
I know, it said 10 to the 4th, but I think there was a typo in the way they did it.
Yeah,
Okay.
it's supposed to be 3.1.
Yeah, if it was 3.1 instead of 31,
Yeah, it works out that way.
okay? But we went with 31, it doesn't matter, it's all how you set it up, okay? I went with what was given. All right, so this right here, so put stars, highlight, if you highlight your notes, whatever, this is super important right here, okay? We need to know how K changes. All right. All right, now, here's the reaction between gaseous sulfur dioxide to form sulfur trioxide. They write an equation, but they give you the equilibrium values, and you just plug them in, okay? That's all you have to do, you just plug them in. So I'm not even gonna go through and do that. And then down here, this is the relationship between Kp and Kc. Again, that's the ideal gas law R, but you no longer have to know how to do that, so we're skipping over that section. All right, now, we're going to look at practice problems in your book. Okay, so. All right, so look. This is page 600 and, I need to put glasses on, I can't read it, it's a shame. 664? 664. Okay, now. We're barely going to get through this, okay, for sake of time, and tomorrow we'll come in and we'll just do more practice. There are 3 ways in which we can calculate the value of K given concentration data. 3 ways, and I'll write them all down tomorrow, but the first way is what we just did, okay? The first way is like number 33. The equilibrium given 2NO plus chlorine goes to 2 is established at equilibrium mixture. The 3 gases have this, this, and this, okay, respectively. Calculate Kp. Well, all you do Write your equilibrium expression, plug in the values given. Okay? Just like we just did in the practice problem previously. All right? So that's the first way. It's just all your equilibrium concentrations are given. There's 3 ways. That's the first. That's the simplest. Don't expect to see that. Okay? It's almost so easy. It's I don't want to offend your intellect. Okay? But we look at number 35. Number 35 is the second way. The second way is you're given initial concentrations and you're asked to find the value of equilibrium, but you're given one equilibrium concentration. And this is where, starting tomorrow, our theme song is going to be playing every day, and it's Ice, Ice Baby. Okay? Anybody got it? Anybody got it for us? Come on. I heard it start. I heard it. Ice, Ice Baby. You definitely don't want me to try and sing it. So, ICE stands for initial change in equilibrium. So we're always going to make an ICE table here. So we're going to have our initial concentration. Now, most teachers have do a completely separate table when you're setting this up and rewriting all the chemicals and all of that. I'm too lazy to do that. Okay? I just do it above the equation. I make it around the equation because I want to see right there what's given. So I stands for initial. What am I given? Well, I'm given a mixture of 0.1 mole, 0.05, and 0.1 mole placed in a 1 liter. Therefore, moles per liter, this is initially, it's 0.1 molar. The H2 is 0.050 molar, and the H2O is 0.1 molar. Because it's that many moles in 1 liter. Now, if it were in 2 liters, I'd have to divide by 2. There's always got to be a molarity. Brackets are molarity. So you got to know what your molarity is. But a lot of times they just say 1 liter and it makes it easy. Or they give you the concentration in terms of molarity. Now, how much nitrogen do they say they put in there? They didn't, right? So how much did they put in? No? No?
Oh, is it inert gas?
No, it is, but that's not the point. 0. If they didn't put any in, they didn't put any in. They just said they put those 3 things in. So it's 0 initially. Okay? So we have ice, and then we have our change, and then we have our equilibrium. So it's ice, change, equilibrium. Ice, ice, baby. Initial, change, equilibrium. Now, in this particular one, they say at equilibrium, NO equals that. Now I can't keep it circled because I don't have space. But my NO is, get this, but it's at equilibrium. K is always equilibrium concentration. It's your equilibrium constant. It's not your initial concentrations, it's your equilibrium concentrations. But I know that at equilibrium, this is equal to 0.062 molar. So how much reacted? If it went from 0.1 to 0.62, what was the change? So minus 0.038 molar is how much that reacted. Right? Because it went from 0.1 to 0.062, which means that 0.038 must have reacted. This minus that equals that. Okay? So how much of this reacted? If 2 reacts with 2, same amount, right? So this was minus 0.038 molar. So how much of this is going to be at equilibrium? 0.012 molar. Well, for every 2 of these that react, how many of these got formed? So what's it going to be? Plus, no, because it's 2 makes 1. So it's plus 0.019. Plus 0, so at 0.019 is how much I'm going to have at equilibrium. What about this one? plus 0.038. So now at equilibrium, I have 0.138 molar of it. So my equilibrium expression, Kc, is going to equal N2 times H2O squared over NO squared times H2 squared. Now I just plug in all of my equilibrium concentrations. We might have time to do that. So N2 is equal to 0.019 times 0.138 squared divided by 0.062 squared times 0.012 squared. Somebody give me an answer super fast. Come on. We got 1 minute.
Maybe 1.4 times 10 to,
Say it one more time.
1.4 times 10 to negative
1.4 times 10 to the minus 5. Does somebody agree with that number?
No. Sorry,
I'm not focused on 0.5 times 10 to
4.1 times 10 to the first.
1.1 times 10 to
4.1 times 10 to the first. Okay, putting it into the calculator is not supposed to be the hard part. Okay, so this is our second type. Our third type is very similar. It's just going to say a certain percent reacted. You give an initial concentration, a certain percent reacted, so that gives me my change. Okay, we'll practice, do those practice ones. You got something different? Okay, hey, nobody, I haven't gotten the same answer from anybody on this one.
6.5 times 10 to the squared.
Oh my god. Yeah.
Okay?
6.5 times 10.
Again, putting it into your calculator is not supposed to be the hard part here. Okay? All right, we'll do more of this tomorrow. Y'all have a wonderful day.
It's 6.5 times.